Hello and welcome. Today we are going on an adventure. We're diving into what I think is one of the most beautiful and just elegant proofs in all of mathematics. We're going to derive the functional equation for the Riemann zeta function. It's a fantastic story of hidden symmetry and pure mathematical genius. So, let's meet the hero of our story, the Riemann zeta function. I mean, look at it. On the surface, it's a pretty straightforward infinite sum. You pick a number, s, and you just add up 1 over 1 to the s, plus 1 over 2 to the s, plus 1 over 3 to the s, on and on forever. Now what's amazing is that this simple formula is deeply, deeply connected to the prime numbers. But there's a catch. Of course there's a catch. This formula only works, it only converges in a very specific part of the complex plane. And that is the big question, isn't it? We've got this incredibly important function, but it's like we're looking at a map of the world where we can only see Europe. What about the rest of it? To really get what this function is all about, we need a map that works everywhere. We need to find a way to extend its definition, a process that mathematicians call analytic continuation.
And here it is. This is the treasure map we're looking for. This is the grand prize at the end of our journey, the Riemann zeta functional equation. Now, I know, it looks pretty intimidating, but its message is actually one of profound, beautiful symmetry. It connects the function's value at any point s to its value at 1 minus s. And our mission today is to build this thing from scratch.
All right, let's get into it. Here's our game plan. First, we're going to meet the key mathematical players we need for our proof. Then, we'll reshape zeta into a totally new form. After that, we'll do something really clever with an integral, unveil the hidden symmetry, and finally, piece it all together into the final equation.
Right. You can't crack a code this tough with just the basics. We need to bring in the heavy hitters. We need two very special, very powerful mathematical tools that are going to let us see the zeta function in a completely new light.
First up, we have the gamma function. You know, if you've ever laid awake at night wondering what 1/2 factorial might be, well, the gamma function is your answer. It basically takes the idea of factorials, 3 times 2 times 1, and extends it from just whole numbers to the entire complex plane. And its properties are going to be absolutely crucial for us later on.
And our second key player is the Jacobi theta function. Now, just like the zeta function, it's an infinite sum. But this one has a secret. It has a kind of magical property, a built-in symmetry, that is, and I'm not exaggerating, the absolute key to this entire proof.
In fact, this property is so important, we should just call it what it is. It's the secret weapon of this proof. Without it, the whole beautiful structure we're about to build just falls apart. It's that critical. And here it is. This is our secret weapon. Seriously, just take a second to appreciate how cool this is. It says that the value of the theta function at some number t is directly related to its value at 1 over t. It's this incredible, almost mirror-like relationship between a value and its reciprocal. And that symmetry? Well, that's what we're going to exploit.
Okay, tools acquired. Now for our first big move. To actually use these new tools, we need to translate the zeta function from the language of sums into a language that's more flexible, more powerful, the language of integrals. And the way we do this is this really neat 3-step dance. We start with a way to write each little piece of the zeta sum as an integral using our gamma function. Then we sum up all those integrals. And when we do that, the zeta function just naturally pops out. And finally, we look at what we've built and we realize the theta function has been hiding inside it the whole time.
So after that little dance, we land right here. We've created this new object, sometimes it's called the completed zeta function, which bundles zeta and gamma together on the left, and it equals this integral on the right, starring our theta function. This is our new base camp, our new starting point for the real climb.
Okay, now for the master stroke. This is the move that makes the whole proof work. We've got this integral that runs all the way from 0 to infinity. And the trick is to do a little mathematical surgery.
We literally just split the journey in two. We break the integral at the number 1. So now we have a piece from 0 to 1 and a piece from 1 to infinity. You might be asking, why there? Well, because that first part, the integral from 0 to 1, that's where our secret weapon, the theta transformation, is designed to work. It's the key that unlocks that tricky first section. So we zoom in on that first piece. First, we deploy our secret weapon, the theta transformation. Then we make a really clever substitution. We say, let's create a new variable u and set it equal to 1 over t. And this move has a fantastic consequence. It completely flips the domain of our integral. The piece that went from 0 to 1 now runs from infinity back down to 1. It's incredible. After a whole flurry of algebra, we put our two integral pieces back together, and we are left with this thing. We'll call it lambda of t's. Now I know what you're thinking. It looks way more complicated than what we started with. But trust me, look very closely at the part inside the integral brackets. Something truly amazing is hiding in there. So here we are. This is the aha moment. That complicated-looking formula is just a mask. Hiding underneath all that complexity is a simple, profound, and absolutely perfect symmetry. We've defined this whole right-hand side as lambda of s. So now for the key question. What happens if we go through this entire expression, and every single place we see an s, we swap it out for a 1 minus s? What's going to happen to the value of the whole thing?
And the answer is nothing. Absolutely nothing happens. That first term, the 1 over s times s minus 1, it stays exactly the same. And that crazy-looking sum of powers of t inside the integral, it also stays perfectly unchanged. It is perfectly symmetric.
And this right here is the climax of the proof. This is the core secret of the zeta function. This completed version of the function, this lambda of s, is perfectly symmetric across the critical line where the real part is 1/2. It's a mirror image of itself.
We found it. We have the hidden symmetry. We have the golden key. Lambda of s equals lambda of 1 minus s. Now, all that's left is to use that key to unlock the final prize, to translate this discovery back into the language of the zeta function itself.
So we write out our symmetry equation in full. Then we substitute back the definition of lambda, which brings our friends zeta and gamma back into the picture. And then, using some classic, well-known identities for the gamma function, we just do a few final algebraic steps to tidy everything up and get zeta of s all by itself on one side.
And there it is, our final destination. A truly remarkable equation that gives us the value of zeta anywhere on that map by relating it back to a value in the territory we already understood. We've built the complete map. We've cracked the code.
This equation is just a monumental achievement. It defines the landscape where the deepest questions about prime numbers live. It tells us where some of the function zeros are, the so-called trivial ones. But it also points to an infinite number of other, much more mysterious zeros. And the Riemann hypothesis, the single greatest unsolved problem in math, conjectures that all of those important zeros lie smack dab on that line of symmetry we just discovered. And proving that, well, that's an adventure for another day.